All right, so make sure you watch the previous video before looking at this one, because this will be a continuation of what we were doing. We were in the middle of a proof and we were doing 2 implies 1. And here I've written our current setup. So our assumption, 2, is that the partials here exist and are continuous. And the partials are this type of map. And we have defined a function g, like this, which is what the derivative of f would be if it existed, right? If the derivative of f existed, then theorem 9.17 tells us what the derivative would be in terms of the partials. So we define g to be that thing that it would be. And when you define g that way, then the pi ij composed with g's end up being the partials, which we have assumed are continuous. So our assumption implies that these are continuous, which by work in the earlier video implies that g is continuous. So we will be done if we can just prove that this g actually is our desired f prime. So that's what we have to do next. So first, fix x in E, arbitrary x in E. Then what we want to prove is that the linear map g of x is f prime of x. So we must prove that 0 is this limit. The limit that I'm going to write down exists and equals 0. And it's this limit as h goes to 0 with this stuff. So I'm just pulling this straight from the definition of derivative. And here I'm putting in the thing that I claim is the derivative, the linear map that I claim is the derivative of f at x, namely g of x. Now, this is a limit of a certain function of h, right? Here we have a function of h. And what kind of function? It outputs m tuples. It's m tuple valued, right? So I can write that in terms of the components. So one way to view it is like this. Sum from I equals 1 to m of, and then the ith component here, and I'll just put the vector, standard basis vector ui here. And here I have the ith component of f, minus the ith component of this vector. So when I do g of x, that's a linear map. When I feed in a vector h, I get another vector with m components, and then here I'm going to take the ith component of that vector. Okay, let me arrange that a little bit better here. Okay, and I think we've discussed this before, trying to swap these two. And not just swap these two, what I'm actually talking about is taking the limit of a vector valued function, or a tuple valued function, and then viewing it as a limit on the individual components. As long as the limits exist, we can do that. And we've made the argument before in, let me find the reference and get back to you. Okay, I found it. It was lecture 3, part 3, around 10 minutes is when we discussed that. And I also just realized that, well, what I wrote here doesn't make sense. And I'm also going to fix something above. Okay, so what I'm saying here is when all the limits that exist, when all the limits involved exist, you can apply the limit operation to the individual components. Like this. And what I want to fix above is, I think I wrote this a little bit confusingly. We must prove that 0 equals this thing. That's true. But the rest of what I'm writing is not what we must prove, right? Only this part is what we must prove. So let's just remember what we must prove. And let me erase this 0 equals. That's what we must prove. And let me say we have that. So we have all of these, as long as the limits exist. So this is if the limit exists. So we have that if this limit exists for all I, then what we're writing works. So let me just write that. Okay, I think it's all right now. So I've written, we have that if all these individual limits here exist, then by earlier comments, limits done at the level of components of a vector valued or tuple valued function tell you about the limit of the tuple valued function. So our goal is to prove that this is 0. Well, to prove that an M tuple, which is what this limit would be if it existed, to prove that an M tuple is 0 is to prove that all of its components are 0. So then we want to prove that these individual components here are 0. So our task now is we must prove this is 0 for all I. So let's fix I, fix one of our i's. 1 through m is the possible range of i's. And then let's examine what is this here. So g of x of h, and then the ith component. Well, g of x of h so g of x of h is g of x of, and then let me write h by expanding it out into, by writing it as a linear combination of the basis vectors. So this will be a sum from j equals 1 to n. And then let's call the components of h sub I, or h sub j here. Like this. So h can be rewritten as a linear combination of these e sub j's. And it's meant to be understood here that when I write the subscript j on h, that means the j component of this n tuple. This is an n tuple. Okay, so hopefully that's clear. And continuing to work with this, so g is linear, right? So that means I can pull out the h sub j here, and the sum. And here I have g x e sub j. And I'm taking the ith component. So that's the same as if I took the ith component at this level. Like this. Just by the definition of vector addition and scaling. And this, by the definition of g, the g that we set up, the ith component, let me put it this way. So this part that I'm underlining in green, what's this? It's the jth column of the matrix representation for g. Then when I take the ith component of that m tuple, I get the position in the ij entry, basically, of the matrix representation of g. So this thing as a whole is dj fi of x. That was the construction of g, was that so that its standard basis matrix representation has this as its ij entry. So here we get the sum of hj times dj fi of x. Okay, so remember our goal? Our goal was to prove that each of these limits is 0, because then the limit of overall here ends up being 0, and that's what we need to prove that g of x is f prime of x. And now I've written this portion here like this, so let me rewrite my goal. So now the current goal is to prove that this limit exists and is 0. So we have fi x, we have fixed I, but my face is in front of it. We have fixed I here, and I'm just copying this stuff over. Plus h here, minus fi x, minus the sum over j, from j equals 1 to n, of hj, and then this partial derivative, the jth partial derivative of fi. Now, the reason I'm rewriting this painstakingly is to show you and hopefully convince you that this entire statement is all about f sub I. So you see the only mention of f here is when it shows up as f sub I here, and maybe I'll just circle it here, and here, and here. There's no other mention of f. So I actually only care about the ith component of f in order to do this. So let me simplify notation. So how about I just define g to be f sub I, which, by the way, is a map from the same domain as the domain of f, but now is into R, since it's picking out the ith component. And then our goal is simply to prove, and it's not simple, but it's simpler than how it was written before, is to prove this. Sorry, I forgot to write equals 0 on the current goal up there. The goal is to show that that limit vanishes. So this is our goal, and this little g I think is a little bit easier to actually work with. And what in the world happened here? This should have said dj g of x. Okay, so now it's just a statement about g. And remember our assumptions. Our assumption at the very beginning is that all partials of f exist and are continuous. So down here, what we know about g is that these partials are continuous. So our goal is to do this knowing that dj g, which is a map from E to R, is continuous for all j. Okay, let's go look at Rudin, and I want to show you which portion of the lecture version of this theorem I'm going to show you. So here's the theorem in Rudin, and let me zoom out here a little bit. Here's the theorem in Rudin, it's theorem 9.21, and I'm using pretty much the same notation as Rudin. And we already did this. This was the 1 implies 2 direction over here, and now we're on the converse, what I'm calling 2 implies 1. So for the converse, Rudin's first step is to say we consider the case m equals 1, and that's sufficient. Why? Well, it's sufficient because of all of this work that we did here. So the work we did here was to reduce ourselves to focusing on g here, where g is real valued. So r here rather than r to the m. So we've done that part. Now, for the rest, usually I'm not just giving you the same proof in the book. I'm trying to find some different way of looking at things just to give you a different, an additional value to what you can see in the book. Usually I try to fill in more details if I can. But in this case, the proof here is quite clean. And every time I try to come up with a different way of looking at it, or maybe something that's more intuitive, it ends up being notationally very involved and messy. So, and every time I try to clean it up, I end up sort of converging on the same proof that Rudin has. So I don't want to just present this to you guys, because you can read it, and you probably should read it. Instead, what I'm going to do is, now that we've reduced to the case m equals 1, I'm going to show you only the case n equals 2. So here, I'm going to say we will only consider the case n equals 2, which is not sufficient. To really see the full story, you need to see arbitrary n, which is handled here. But I think with n equals 2, you can see the important steps, and it's a lot more intuitive, I think, what's going on. Or at least I can write out everything. And I think if you see the lecture version with n equals 2, then the steps Rudin takes will make a lot more sense, because you can view them as, oh, how do I generalize this to higher n? Okay, so that's my reasoning for only considering n equals 2 in lecture. Okay, so n equals 2 means g is a function of 2 variables. So that means over here, this sum is only a sum of 2 terms. So let me rewrite this thing over here with that in mind. And I'm going to start by copying and pasting. So let me just come back to you when I have everything arranged. Okay, there it is, pasted. So here's our goal. And this is now just 2 terms. So the first term is h1, the first component of h. H will be a 2 tuple, just an ordered pair of numbers. h1 times d1 of g of x minus h2 d2g of x. So that's now our goal. And it's a limit statement, so let's begin. Let epsilon be greater than 0. And now we want delta, a delta that works. And instead of leaving delta unknown, I'm going to use the delta that I stole from Rudin. And let's just see if we can convince ourselves that it works. And hopefully as we go through it, initially the delta will look really random to you, but as we go through it, then you might see where one might have gotten that delta. So there is some delta greater than 0, such that then I'm going to require 3 things here. First, I will require that that the ball of radius delta centered at x. Remember, x is fixed throughout this entire thing. Like way up at the beginning, we fixed x, in case you forgot. X was fixed, and we're trying to show that the derivative of f at x is g. Okay, back to this. So the first thing we want delta to do is that the ball of radius delta centered at x is a subset of E. And we can do this because E is open. So here E is open. So there is a delta that makes this happen. And then number 2, we want for all y in the ball of radius delta centered at x that d1g the partial derivative of g with respect to its first variable of y compared to d1g of x we want that distance to be less than epsilon over 2. And what am I using here? The continuity of g. Of d1g. So our main assumption up here is that the partial derivatives of g are continuous. So d1g is one of the partial derivatives, and so it's continuous. So this we can do because d1g is continuous, and specifically I'm using continuity at x. And the third thing here is the same as the second thing, but for d2g. So for all y within delta of x, d2g y compared to d2g x, the distance is less than epsilon over 2. And now I'm using this fact that d2g is continuous at x. So the delta that I'm choosing here is the minimum of 3 deltas. First I'll get like a delta 1 from the openness of E, a delta 2 from the continuity of d1g, and a delta 3 from the continuity of d2g. And then this will be the minimum of delta 1, delta 2, delta 3 will be the delta that I choose here. And what this delta needs to do, the job that it needs to finish, is to make this thing, whose limit I'm taking and trying to show it's 0, be less than epsilon in norm. So let's see if this delta works as a response to this epsilon. So let h be within delta of 0. Let me write it like this. Let h be such that, let h in R2 be such that the norm of h is greater than 0 and less than delta. Then we want to prove that the norm of this thing up here is less than epsilon. And I'm just going to focus on the numerator, the norm of the numerator. So now my goal is to show that the norm of the numerator is less than epsilon times the norm of h. So I'll think of it that way. Okay, now let's think about this. I'm trying to show this is less than epsilon times the norm of h. So let's think about this. So let's think for a second as though we are students in calculus or in math 6a or something. G is a function of 2 variables, and here's x, and I'm thinking about the difference between g of x and g of x plus h. So here's maybe x plus h, and h is this displacement vector. And I'm trying to approximate the change from in the value of g from x to x plus h by using derivatives. And all I've got showing up here is partial derivatives. So here I've got the first partial, like the derivative of g with respect to its first variable, at x. So this one is really only telling me, like this rate of change. This is like the rate of change of g in the horizontal. Let's say the first variable of g is along the horizontal axis, and the second variable is along the vertical axis. This is telling me the rate of change of g as I move horizontally, right? It's like dE1 g. It's that directional derivative at x. So it's telling me how g changes as I start at x and move horizontally in the E1 direction. So when I multiply it by h1, it's estimating if I move just along the one component of h, what's the change in the output of g. So let me put it this way. Let me use some colors. So I think that, let's say green, that this represents kind of, or estimates the change from here to there in the value of g. So this is like delta g along here. It's an estimate of that. This, on the other hand, let me use a different color, red. This, on the other hand, is an estimate of delta g along here. Now, how is that supposed to tell me about how g changes as I go from here to there? Well, the way I think about it, they're not so different. The estimate of delta g along here versus along here cannot be so different considering that this partial derivative is continuous. So that's one way to think about it, although when I was thinking about it that way, I couldn't write a non-terrible proof, a non-messy proof along those lines of thinking. But I hope this picture is going to help motivate the next step. Okay, so understanding how to move the red line kind of from here to here is quite complicated, and I want to leave that for after we look at this, how to handle this green line. Then at that point it'll seem like there's just one thing we can do that makes sense. So this green line, the delta g along that displacement vector is what this is estimating. And so to write that more precisely, this kind of estimates g at x, g here minus g there. So g here is g at x plus h1 e1. And then g there is g at x. So this part estimates this. By estimates, I mean when h becomes small, this becomes close to this. That's sort of the point of a partial derivative, right? What we have here is not this. Instead of an x plus h1 e1, we have x plus h. So I'm going to do this trick that comes up often in analysis where I add and subtract something in order to get the thing that I want to show up. Okay, so let me clean all the annotations off of here and I'll be right back. Okay, so I'm going to write equals, this thing equals, and then I'm going to write what I wish it were. I wish it were h1 e1 here. And then I'm going to add and subtract stuff to correct for what isn't true about what I'm writing. Okay, let me clear out more annotation. Okay, so we're like that. And then, so to make this true, I should include let's see, so why can't I stop now? Because first of all, I've written this instead of this. So I need to add on this still, and then remove this term that I added. And I never added this term here, so let me add that in. Okay, and you should be able to read this line and check that it's still good. It's just algebra, adding and subtracting some terms. Okay, and I also want to write this a little bit differently. So instead of g of x plus h, I'm going to use the fact that h is h1e1 plus h2e2. So this is g of x plus h1e1 plus h2e2. So it's like that, plus here. Okay, now this portion here looks like it would be small when h is small. Looks like we can make it smaller than, any epsilon we want times the norm of h. The norm of h1, rather. Just because of the definition of this partial derivative. And same for this portion. It looks like we can make it small. But if you think about trying to choose a delta to make things work, it's not so simple. Part of the issue is trying to move that red segment, line segment that I was drawing, over. Trying to move that vertical line segment over. That's part of what makes this difficult. So one trick that is helpful here that makes things work and uses the full power of the fact that the partials exist everywhere, the partials of g exist everywhere, is the mean value theorem. So we're going to try to bring the mean value theorem into this. We will apply the mean value theorem to try to write these two portions here and this one in terms of the derivative of a thing at a point. So first I need to describe exactly what is the mapping that I'm going to apply the mean value theorem to. So for the green one, let me stick with the color coding here. Focus on this mapping from theta. I'm going to call the parameter theta, like Rudin does. From theta to g of x plus theta e1. So consider this mapping. Consider the function mapping theta to this defined on, so it's defined from 0 to h1, or from h1 to 0, depending on whether h1 is positive or negative. So 0 to h1, or h1 0, depending on which one makes sense. Now, this mapping, it's a mapping from this domain, 0 to h1 or h1 to 0, to real. So it's a real-to-real type function. And it's differentiable. This is differentiable. And actually, before I talk about differentiable, how about let's verify that it exists, that it makes sense to evaluate g at these values. So let me bring the picture back in for a moment. So here we have x, and here's our ball of radius delta. And somewhere you've got h, x plus h. So there's this displacement vector, h, that goes with it. Then h has a horizontal component here, which is h1, e1. And it has a vertical component, which we'll probably have to look at in a moment, which is h2, e2. Then this mapping, if I look at theta, if I look at these for all values of theta between 0 and h1, then I'm just looking at the points along here, right? And since h1, e1, well, since h since h is less than delta like this, h1 is less than delta, right? A component is always less than, in length, is always less than the length of the overall vector. So this point is definitely inside the delta ball centered at x. And since x is the center and this point is also in there, any point along the segment connecting them is also in there. In fact, the delta ball is convex. So if we use the fact that delta ball is convex, that balls are convex in general, Euclidean balls are convex, then any 2 points you have in there, all the points on the segment joining them are going to be in there. So here x is in here, and h1, e1 is in here, so all the points on the segment connecting them are in here. So these points are all in this ball. So they're in the domain of G, because they're all in E, in the set E. Remember, one of the properties of our ball was that it's inside E. And so this is a perfectly good function. It makes sense as a function. And what I'm trying to say now is it's differentiable. And the derivative, so if I do d theta, gx plus theta e1, and let's say I evaluate at a certain theta equals theta naught, then that is what it means. That's a certain directional derivative of g, right? That's what it means to say d1 g of x. Well, it's d1 g. If I evaluated at theta equals 0, I would get d1 g of x. But evaluating at theta equals theta naught would give me d1 g of x plus theta naught e1. So I'm not just talking about differentiability of g at x, I'm talking about differentiability of g at other points too. Partial differentiability in the sense of partial derivatives. Okay, so now apply the mean value theorem. There's some, let's call it theta 1, following Rudin's notation in his proof. So there's some theta 1 between 0 and h1, and I'm using this phrase between because I don't know if h1 is positive or negative, so this sort of remains agnostic about that, such that and I'm applying the mean value theorem to this mapping, so such that g of x plus h1 e1 minus g of x plus 0 e1, I'm applying it on the region 0 to h1, or h1 to 0, equals my derivative, so that's d1g x plus theta 1 e1 times h1 minus 0. So times h1. So this is what the mean value theorem gives me. And I'm going to do a similar thing to the red segment here. So I've applied the mean value theorem along this green line segment, and now I'm going to apply it along the red line segment. So this one is a little bit more complicated to write down. So consider the function theta goes to g of x plus h1 e1 plus theta e2, defined on 0 to h2 or h2 to 0, whichever one of those makes sense. Then, like we just argued, all the points along this line segment, since this point here is in the delta ball And this point is in the delta ball. All the points along the line segment are in the delta ball. So this is a perfectly good function. And it's differentiable. So that's worth writing down. The derivative with respect to theta of this function if I were to evaluate at theta equals theta naught, then that's d2g at x plus h1 e1 plus theta naught e2. Okay, so now by the mean value theorem, there is some theta 2, following Rudin's notation, between 0 and h2, such that gx plus h1 e1 plus h2 e2 minus the same. So this function here evaluated at theta equals h2, and then I have to subtract the same thing but evaluate at theta equals 0. That's how the mean value theorem works. Equals, and then my derivative, this thing, times h2. Times h2, and that went off screen. Let me move it there. Okay, so what I've done is use the mean value theorem. So here I am. This is the thing that I'm trying to show is less than epsilon times norm h. And what I've done is use the mean value theorem to replace the green part here and the red part here. So how about I go back here and copy and paste all of this stuff, and then continue the calculation. So I'll copy this. Okay, I'll be right back. This is a little finicky. Alright, zooming out seems to help. So I'm copying it and putting it down here. And actually, I'm running way out of room here. So maybe what I'll do is move it up here. So continuing. Okay, I don't know where these came from. But continuing from here. I have this now. So the green part is now d1 g x at x plus theta 1 e1. Times h1. And then the red part is d2g x plus this doesn't make any sense. Okay, let me fix that. X plus h1 e1 plus theta 2 e2 h2 minus this thing. Okay, let me stop with the colors. So now I have h1. Let me pull out the overall h1 here and use the triangle inequality. So I have h1 here, and then here I have d1g x plus theta 1 e1 minus d1g x. Hopefully now you're seeing why continuity of the partials matters. And here d2g x plus h1 e1 plus theta 2 e2 minus d2g x. And remember, h is less than delta. Here h is less than, well, no, that's not what matters. Well, it does matter. So since h is less than delta, we know that this, okay, so I want to apply continuity of d1g and d2g, right? Let me go back to what delta achieved. So if I go back to the three things delta had to do, number 2 was for all y in the delta ball centered at x, this difference is less than epsilon over 2. And then similarly for d2. So going back here, in order for that to apply to our situation here, we need that the distance between this point here that's being input into d1g and x, we need that to be less than delta. In other words, we need this to be a valid y for that property over there. Now, the distance between this and x, so let me go back to that picture. This here is a point on this green line segment over here. So x plus theta 1 e1 is some point along this line segment, somewhere here. That's because theta 1 was supposed to be between 0 and h1. And the other one, the other point I'm going to point out is somewhere along this line segment, somewhere here. That one is this. X plus h1 e1 plus theta 2 e2 is just somewhere along that red line segment. So they're both inside the yellow delta ball in the picture. So then, this is less than epsilon over 2. This one is less than epsilon over 2 plus h2 epsilon over 2. And of course, a component of h is always going to be less than h, right? hi, absolute value, is always going to be less than the norm of h as a vector. There's some screaming outside. Not sure what's going on. Okay, so this is less than or equal to norm h epsilon over 2 plus norm h epsilon over 2 is norm h epsilon. And that is victory. So that is victory because our goal way back here was to show that this limit of this thing divided by norm h is 0. So we're trying to show that this thing here is less than epsilon times norm h. And that's what we reached. Okay, that was fun. So again, this is only the case n equals 2. So I guess I don't have the right to put a box here. Let me put a box with 2 in it to say we only did the case n equals 2. And if there's one thing that I would say should stick with you from this proof, definitely not like the most memorable proof, but something should stick with you, which is the stuff going on in this picture, specifically the fact that we needed to know not only about the differentiability, we needed to know not only about partial derivatives at x, but we needed to also know about partial derivatives along these lines. So we needed to know about partial derivatives away from x. And ultimately, in the end, we needed not only their existence, but their continuity. But that's what's really special, I think, about what's going on in this theorem is our final conclusion is a conclusion about differentiability of f at x, right? Our final conclusion is our original f is differentiable at x. But to do it, we needed to know about partials and their differentiability along these lines away from x. That's what we needed to apply the mean value theorem back here. So I would say that's the main thing to get out of this theorem.